I'd like you to recall the last time you stood and gazed up at the dark night sky. 1,000 scattered pinpricks of light, and perhaps the sweep of the Milky Way. I don't know about you, but I'm always struck by a profound feeling of antiquity. The night sky feels so unchanging. Several thousand years ago, people looked up upon the very same stars and constellations and gave them the names we know so well, Orion the Hunter, or Andromeda the Maiden. But just as some aspects of nature occur too quickly for us to notice, other aspects occur too slowly. As the hours pass, the sky wheels round. As the weeks pass, the planets wander. And as the centuries pass, the stars slowly drift. In fact, the dinosaurs would not have seen the same constellations that we see today. But what about an image like this one? Do galaxies move as well? And if so, how? The answer is yes, they do, and in three quite different ways. First, there are internal motions. As their spiral patterns suggest, many galaxies rotate, each turn taking perhaps 100 million years. Second, there are local motions. Galaxies are pulled by their neighbours' gravity this way and that, which may cause them to gather into groups or even collide with each other. Now, both these kinds of motion are relatively slight, no more than a few hundred kilometres per second. But there is a third kind of motion called cosmic expansion, which only becomes apparent across much larger distances. All galaxies appear to be moving away from each other, and perhaps surprisingly, at greater and greater separations, this expansion motion is faster and faster. It's the nature of this cosmic expansion that's the subject for this lecture. Now, it's all very well me telling you that the galaxies are moving, but how do we know that? How do we measure their motion? In fact, it turns out to be surprisingly easy. You carefully study a galaxy's spectrum. Remember from lecture 4 that light is an electromagnetic wave where different colours correspond to different wavelengths. The key to measuring an object's motion is illustrated in this little animation. If an object is moving towards you, the waves get scrunched up, so we witness shorter wavelengths or bluer colour. We say the light is blue shifted. On the other hand, if the object is moving away, the waves get stretched out and we witness a longer wavelength, a redder colour, which we say the light is red shifted. Now, this effect was first understood in 1842 for sound waves by the Austrian scientist Christian Doppler. Now, for sound, shorter and longer waves correspond to higher and lower pitch. And the so-called Doppler effect is famously apparent when something like a car passes us by. We have towards us shorter waves, higher pitch, away from us longer waves, lower pitch. Now there's a simple formula which gives the speed of the object from its change in pitch for sound, or in our case, the change in colour for light. The ratio of the speed of the object to the speed of the wave, so that's v over c, where c, as always, is the speed of light, is equal to the change in wavelength over the emitted wavelength, which we write as delta lambda over lambda, where lambda is the physicist's usual symbol for wavelength. For example, if an object is moving away from us at 1% of the speed of light, so that's 3,000 kilometers per second, that's across the United States in 1 second, and it emits green light with a wavelength of 500 nanometers, then we see those waves that are 1% longer, and they're 505 nanometers, which is a very slightly redder version of green. Now, could we detect such a small change in colour? The answer is yes, and here's how. Remember, also from Lecture 4 that the hot atmosphere of stars emits a broad range of colours, a thermal spectrum, like the one here. Now, for a smooth spectrum like this, it would actually be quite difficult to detect a small 1% shift in wavelength. But nature is very kind to us, and within the star's atmosphere, atoms leave their mark on the spectrum by absorbing and emitting specific colours. These sharp features are called spectral lines, and they act very like an accurate wavelength scale. And it's fairly easy to see quite small Doppler shifts in their position. This example shows the spectral lines coming from hydrogen atoms. The middle spectrum shows a redshift of about 1.5%, so that's 4,500 kilometers per second, and the lower spectrum shows a blue shift of about 2%, or 6,000 kilometers per second. Now, historically, some of the earliest attempts to measure the Doppler shifts for galaxy spectra were made around 1916 by Vesto Slipher at the Lowell Observatory in Arizona. For 15 nearby spirals, he measured velocities of a few hundred kilometers per second. And although the Great Andromeda Galaxy M31 was approaching at 300 kilometers per second, in almost all the other galaxies were redshifted, showing they were moving away from us. Now, this work of measuring galaxy Doppler shifts culminated in the late 1920s when Edwin Hubble and his assistant Milton Humason used the 100-inch telescope at Mount Wilson to measure many more Doppler shifts, and most importantly, also galaxy distances, using rather less precise methods than the ones we looked at last lecture. Now, I'm going to come back to Hubble's famous discovery in a minute, but I just wanted to show you some of the observational methods used to measure galaxy spectra. So crucial to this work are spectrographs. These are instruments that take the light from the telescope and spread it into its many colours. Here's a picture of Slipher's spectrograph and a sketch of what's inside it. Two prisms each disperse the light from the previous one and ultimately spread the incoming white light into a band with red at one end and blue at the other. Now, in the 100 years or so since those times, spectrograph design has come a very long way. Today we use diffraction gratings to disperse the light rather than prisms. You can see here they act a bit like mirrors that reflect blue light at a slightly different angle to red light. Today, the world's largest telescopes are equipped with multi-million-dollar spectrographs that are often much bigger than the astronomers who use them. And just to give you an idea of how far we've come, Hubble sometimes needed over 80 hours of exposure time spread over several nights to observe his faintest galaxies. Now today, a big telescope and a modern spectrograph observing the very same galaxy can yield a comparable spectrum in less than a minute. So 80 hours to 1 minute. That's a huge improvement. So here's some spectra of a few galaxies. From blue on the left to red on the right. Notice how the overall shape of the spectrum match the colour of the galaxies. Galaxies which appear yellow or orange have spectra which slope up to the right, or red. And then galaxies which appear blue have spectra which slope up to the left, or blue. But much more importantly, notice the absorption and emission lines in the spectra. It's the position of these lines that reveal the galaxy's Doppler shift. As you can see here, the top spectrum is essentially unshifted, while the very same lines appear in the lower spectrum, and they're all clearly shifted to the red, in this case by about 14% in wavelength, which corresponds to a huge velocity of 42,000 kilometers per second. That's twice round the world in 1 second. Now, here's the crucial thing to notice from this figure. The stationary galaxy is clearly quite nearby, while the galaxy with the high redshift is clearly much further away. It's this association between the amount of redshift and the distance that Hubble discovered. And that is so important. So let's have a look at that now. Here's the actual plot published by Hubble in 1929 that suggests a correlation between distance, that's along the x-axis, and speed, that's up the y-axis. By 1931, Hubble and Humason had used a slightly different approach to measure much more distant galaxies, and the correlation gets much clearer. Here's a more recent version of the plot, which incorporates most of the distance ladder methods that we met in the last lecture. Now, in all these graphs, there's a straight line, proportionality, between distance and recession speed, so that a galaxy with twice the distance is moving twice as fast, and a galaxy 3 times the distance is moving 3 times as fast, and so on. Now, this relation is called the Hubble law, and it tells us that the entire universe is expanding. Now, mathematically, the Hubble law can be written: velocity equals h naught times distance, where h naught is called the Hubble constant. It's just the gradient of the straight line. Remember, the gradient of a line is the ratio of a vertical jump to a horizontal jump. So in this plot, with velocity in kilometers per second and distance in megaparsecs, the gradient, h naught, is 72 kilometers per second per megaparsec. But using more familiar units, that's 22 kilometers per second per million light years. Now, what this tells us is that for each additional million light years in distance, a galaxy's velocity is 22 kilometers per second greater away from us. Now, although this modern diagram doesn't look much better than Hubble's 1931 diagram, it is in fact vastly improved. Because although Hubble got the straight line correct, his x-axis, the distances, were incorrectly calibrated and were 10 times too small. So his gradient was 10 times too big. Now, getting those distances measured and properly calibrated has been a very hard task, and it's taken 60 years to finally get the uncertainties below about 10%. So we now know that the Hubble constant is 22 plus or minus about 2 kilometers per second per million light years. Now, this diagram should make the Hubble law seem more real to you. We're at the apex of the cone, which contains 100,000 galaxy positions out as far as 2 billion light years away. And the arrows show some representative galaxy velocities. Now, this is an amazing pattern. All galaxies are moving away from us, with more distant galaxies moving faster. The whole pattern is called the Hubble flow. Now, this Hubble flow has 3 lovely properties that I want to tell you about. So first of all, the most striking aspect of this velocity pattern is it really seems as though we occupy a special location. All the galaxies seem to be moving away from us. What's wrong with us? Or, more seriously, perhaps the Big Bang occurred right here nearby our galaxy. Well, before you jump to conclusions like that, let's first ask a very simple question. What does the Hubble flow look like to someone living in another galaxy? So, here we're on galaxy A, witnessing the Hubble flow. Now, to get to B's perspective, we need to jump from A to B and then run along with B. And when we do that, the velocities change. And so from B's perspective, this is what they become. Galaxy B witnesses an identical Hubble flow. In fact, the same is true for all galaxies. They all witness a Hubble flow. Now do you see why there is no single center to the expansion? In fact, one could say that every galaxy feels to be at the centre, with all the other galaxies moving away from it. But in truth, all galaxies are moving away from all other galaxies, and the universe as a whole is expanding. Now, this is actually a great example of the universe obeying the cosmological principle. Remember that we met back in lecture 3. Remember, it says that the universe appears the same from all locations. Now, in this context, everyone sees the same Hubble law. Now, at this point, I'd just like to clarify something that's potentially confusing. The expansion only occurs between galaxies. The galaxies themselves are not getting bigger. Gravity can easily overcome the expansion locally, but globally, the entire system is expanding. Okay. Now, the second conclusion from the Hubble law is that as time passes and the expansion proceeds, the universe becomes emptier. And conversely, in the past, it was more crowded. In other words, the universe as a whole is changing. And so we might expect it to be radically different in the distant past, or also in the distant future. Now, the third conclusion stems from the simple proportionality of the Hubble law. If we run the clock backwards, the nearby, slowly moving galaxies arrive at the same time as the more distant, fast-moving galaxies. In fact, all galaxies arrive on top of all other galaxies at the same moment. This, of course, is the moment we call the Big Bang. It's when the expansion began. In fact, with just a bit more effort, we can use this expansion to estimate the time since the Big Bang. In other words, the age of the universe. It's really very simple. Take a galaxy at a distance of 1 million light years. We know from the Hubble law that it's moving at 22 kilometers per second. So here's the question. How long did it take to travel those million light years moving at 22 kilometers per second? The math is identical to asking how long it takes to travel 120 miles moving at 60 miles an hour. You take the distance and you divide it by the speed, and you get, in that case, 2 hours. Now, in our case, we have 1 million light years, which is about 10 to the 19 kilometers, and we divide it by 22 kilometers per second, which gives a journey time of about 4.3 times 10 to the 17 seconds, or about 13.5 billion years. Now, notice that it doesn't matter which galaxy we choose. One that's twice as far away moves twice as fast. So the division gives the same result. So this is our first estimate of the age of the universe. The Big Bang occurred about 13.5 billion years ago. Now let's just redo that math slightly differently. Using the Hubble law, V equals h naught times d, we can substitute in here for V. Now notice that the d's cancel, and we have the lovely result that our age estimate is just 1 over the Hubble constant. Perhaps not surprisingly, astronomers call this time the Hubble time, and it's written TH. This also gives us an estimate for the size of the visible universe. Remember, we can only see as far as light can travel since the Big Bang. So that's just the Hubble time, TH, multiplied by the speed of light, c, which is also c over h naught, and it's obviously 13.5 billion light years. And it's usually written RH and is called the Hubble radius. Now you can see why measuring the Hubble constant is so important. It feeds directly into measuring the age of the universe and to measuring the size of the visible universe. Now, you may have noticed I've been rather careful to say that the Hubble time is only an estimate for the cosmic age. Why might the true age be different? Well, in our calculation, we made a very big assumption. Galaxies move at constant speed since the Big Bang, which is probably incorrect. If you think about it, as the mass pulls back in during the expansion, it's likely to slow down, and that will change the age estimate. Now, these graphs show the various possibilities. Both have time along the x-axis. The top one shows the distance to a galaxy that is today 1 million light years away, and the bottom one shows its speed. So for a constant speed of 22 kilometers per second, we have the green lines. The distance was 0 at the Big Bang, a Hubble time th ago. The gradient of this line, that's this divided by this, is constant and gives the speed 22 kilometers per second. Now, these orange lines show an expansion that starts out fast and then slows down, so it's decelerating. Obviously, since it was travelling faster in the past, then the total journey time is shorter, and so the cosmic age is less than a Hubble time. And then lastly, these blue lines show an expansion that starts out slowly and then speeds up. It's accelerating. Since it was travelling slower in the past, the overall journey time is longer and the cosmic age is greater than the Hubble time. So, what's the situation for the real universe? Well, by looking far away and back in time, it's possible to measure how the expansion rate has changed over cosmic history. And as we'll see in later lectures, it's found that both situations have occurred. The expansion started out fast and slowed down, then it sped up and is currently accelerating. And by chance, the periods of deceleration and acceleration nearly cancel out, so the actual age is surprisingly close to the simple Hubble time. It's just 2% bigger at 13.7 billion years. So the original rough estimate of 13.5 billion years turns out to be not so bad after all. Now, as you've just seen, we've used the observations of the cosmic expansion, the Hubble law, to first approximate and then actually refine an estimate for the age of the universe. But this is such a crucial measurement that it's extremely important to find independent estimates for the universe's age. For example, if we found a star with a measured age of 100 billion years, we'd know something was seriously wrong somewhere. On the other hand, if independent estimates also suggest 14 billion years, then the Big Bang theory is hugely strengthened. So let's look briefly at an alternative estimate for the universe's age. Actually, what's done is to measure the age of our galaxy, because, as it turns out, it formed soon after the Big Bang, so its age should be close to, perhaps a little less than, the true cosmic age. Now, there are actually several different ways to measure the age of our galaxy, but the most well-known and accurate way is to measure the age of star clusters using a technique called main sequence fitting. So let's look at that method now. Main sequence fitting relies on the fact that a star's lifetime depends on its mass. Now, stars are born in large groups or clusters, thousands at a time. They're all very similar except for one quality. They have different masses. Now, more massive stars are also brighter. It's not too difficult to see why. Their greater weight presses down, making their nuclear furnaces burn more vigorously, and so the star's more powerful. Now, to follow the subject, I want to use a famous diagram introduced by the Danish and American astronomers Hertzsprung and Russell around 1913. This kind of diagram arranges stars by their colour along the x-axis and by their luminosity up the y-axis. So this illustrates the HR diagram for a very young cluster of newly born stars. Notice how the stars fall along a diagonal line from feeble red stars of very low mass at the bottom right up to powerful blue stars of very high mass at the top left. This famous diagonal line is called the main sequence. Now here's the crucial part. The more massive stars, being more powerful, burn up their fuel fastest and die first. So as time passes, the main sequence gradually erodes from the top down as less and less massive stars use up their fuel, die and leave the main sequence. So the length of the main sequence acts as a kind of clock. The shorter the main sequence, the older the cluster. Now, of course, this clock still needs to be calibrated in actual years, but, and you'll just have to trust me on this, the lifetime of stars are well understood, and the clock is in fact well calibrated now. So here are a few examples of real star clusters. The HR diagrams. This is a young cluster with its long, full main sequence. Here's an older one that's already lost much of its upper main sequence. And here's one of the galaxy's oldest clusters. Now let me just summarize the results of these kind of studies. In the disk of our galaxy, we find relatively young clusters ranging from newborn to about 9 billion years. But the surrounding halo contains a truly ancient population of star clusters with ages from about 10 to 14 billion years. Now, this is exactly what we'd hoped for. The oldest clusters approach the cosmic age and must have been formed shortly after the Big Bang. But most importantly, there are no clusters much older than 14 billion years. Now, a slightly cruder version of this method can also be applied to other galaxies, and we always find the same result. Ages can approach 14 billion years, but they never go over. So this agreement between the expansion age with the age of the oldest things we find in the universe really provides very strong support for the whole Big Bang story. Now, I want to end this lecture by refining our perspective of what redshift actually is. You see, so far, I've just described it as a Doppler shift due to a galaxy's motion through space away from us. But a more mature perspective sees galaxies fixed in space, and it's the space that's expanding, carrying the galaxies along with it, rather like expanding dough in a raisin cake carries the raisins along with it. In this view, redshift occurs because the light waves are stretched as they cross through the expanding space. Now, this perspective leads to an extremely useful result. Imagine a photon of light leaving a galaxy. As it's traveling through the universe, both the universe and the photon get stretched by the same amount. So we have a very simple relation. The redshift stretch factor, which is the ratio of the wavelength that we observe to the wavelength that was emitted, is the same as the cosmic stretch factor, which is the ratio of the distance to the galaxy now to the distance to the galaxy when the light set out. So now do you see that the redshift of light tells us by how much the universe has expanded since the light set out? Now here's a real example from one of the galaxies I happen to be studying. It's relatively nearby, roughly 700 million light years away, and its spectrum is shifted about 5%. So the hydrogen line at 486 nanometers is shifted to 510 nanometers. Now, since the photon was stretched by 5%, we know the universe was also stretched by 5% during the photon's journey. So we've just learned that 700 million years ago, when the first multicelled organisms were evolving on Earth, the universe was 5% smaller than it is today. Well, we've covered some important things in this lecture, so I'd just like to briefly review. Spectra of galaxies appear shifted to the red, showing they're all moving away from us, with more distant ones moving proportionately faster. This Hubble law suggests a cosmic expansion that started in a Big Bang. The gradient or slope of the Hubble law is called the Hubble constant, and its value is 22 kilometers per second per million light years, with about a 7% accuracy. If we assume constant expansion, then 1 over the Hubble constant gives us an approximate cosmic age of 13.5 billion years. But this gets refined to 13.7 billion when we allow for the decelerating and accelerating stages of the expansion. This age nicely matches completely independent methods that measure the ages of the oldest star clusters in our galaxy, and with less accuracy, the ages of other galaxies. Finally, we modified our view of galaxies hurtling through a static space to one that views galaxies embedded in an expanding space, being carried along in the flow. Light waves moving through this expanding space are stretched, with a stretch factor that exactly matches the cosmic stretch factor. This is perhaps the first time we've encountered space, the framework itself, as an active, live character in the story. But stay tuned. That's only the beginning. Space, it transpires, will return time and time again to take center stage.